Hi everyone. Okay, we're in question 18 of the revision summary on the 32 questions sheet, and I'm going to try to go a little bit quicker because in trying to explain a little bit of every question and going into theory a bit, this has turned into a bit of a marathon of making videos that are a bit too long. So I'll go a little bit quicker, and that way it won't take you 6 hours to go through all the videos. Okay, so on question 18, it said a skydiver has a mass of 75 kilograms, so mass of 75 kilograms, and at 18 miles an hour. I'm not going to use miles an hour, I'm going to use kilometers because that's what we're going to get in exams. So we're going to say it says at 80 kilometers an hour the drag force on the skydiver is 650 newtons. Find the acceleration of the skydiver at 80 kilometers per hour. So G is 10 newtons per kilogram, which is the same thing as 10 meters per second squared. When you see G like this equals 10 newtons per kilogram, don't worry, it's exactly the same thing as 10 meters per second squared. They are the same thing. Okay, this one just talks about the gravitational field force, which is how many newtons each kilogram feels, and the other one talks about the acceleration, but they're both the same, equivalent. We'll talk about a bit more about that next year. Okay, so these are the same, and that's the mass, and they give us a speed or a velocity down, which is 80 kilometers per hour. And so they tell us that at that speed the drag force, so force of drag of the air, otherwise known as air resistance, is 650 newtons. So they tell us to at that speed, this is the drag force, right? The quicker you go, the more the drag force is. So that's why they've got to tell us at that speed, that's what the force is. And they say, so find out the acceleration of the skydiver at that speed. So we don't really need the speed anymore. They've already told us that this is the speed, and they've told us that at that speed, this is the force. So that's what's important, to know the force going against him. So here's the guy. Looks something like that, and he's falling, and he's got his backpack here, and he's falling down, and we know that he's got two forces acting on him. One of them is the weight, which is mg, mass times this or that, and the other one is the drag force, which is given to us, F drag, which is given as 650 newtons. So what's our formula for acceleration, which is the one we want to find? Here they ask us for the acceleration. Formula for acceleration in this case is F equals ma. You also have the other formula for acceleration, just as a reminder, v minus u over t. So change in velocity divided by time. But here they don't tell us the time it takes and the speed increase or anything. They just tell us the forces. So we've got to use this one here. What's this force? The net unbalanced force. So that means the difference between this one and that one is the unbalanced force, and that will give you the acceleration. It might be 0 if they're both the same, we don't know, and then the acceleration would be 0. So that would be if this is 0, then this would also be 0, right? If that's 0, that's also 0, because the mass is not 0. So let's then work out what the resultant force is, or the net force, and then we can find out the acceleration. So we need this, we need the weight. Weight is 75 times 10, so that's going to be 750 newtons down. So the difference between 750 down and 650 up, that's going to equal our mass times our acceleration. So that's our resultant force, is all of that. So when we do that, we get 100 of spare force that we have left. It's equal to ma. We divide both sides by m, or this is the m multiplying on this side, so we bring it to the other side dividing, and since its mass is 75 kilos, we bring it here and we get our acceleration. So let's see, what's 100 divided by 75? 1 1/3. So 1.33 to 3 significant figures is meters per second squared is the acceleration that the guy is going to fall with when the drag is this much. And this is important also to note, as he keeps on going faster and faster, here there is still some acceleration, meaning that he's going to increase his velocity more and more going down. As that happens more and more, the drag force will get bigger because it's proportional to the velocity. The more you push on the air, the more the air pushes back on you. Eventually we'll get to a point where the weight is equal to the drag force, and then you will have something called terminal velocity. In other words, the velocity beyond which it doesn't increase anymore. You would get that when the weight is equal to the force of drag. So that will happen when the force of drag is equal to 75 times 10. So when the force of drag equals 750 newtons, in this case, when the guy weighs 75, that's when he will get to terminal velocity. Okay, so that was question 18, and let's move on to question 19. I try not to get muddled up with stuff and go quickly, but seems like there's a lot of stuff to mention. I get a bit bogged down with the details. Write down Newton's third law of motion and illustrate it with a diagram. So Newton's third law is one of the simplest, but probably one of the most tricky ones also to visualize. I've mentioned it before, and basically the law says that every force has an equal size but opposite direction counterforce. Okay, and the important thing here, if you saw the other video, I already mentioned it, is that these two forces, which are called Newton pairs of forces, these two forces act on different objects. So you've got to realize that. So if you're standing like this and you're pressing on a wall and you're pressing in with 50 newtons, then if you're not accelerating, in other words, you're not moving through the wall, then the wall is pushing back on you with 50 newtons. Right? And you might say, okay, but when I punch something, if I've got I'll try to think of a non-violent example. If I punch I don't know, a piece of pie or something, some food, then this is my fist and I punch it, then obviously this is going to be much more damaged than my hand. But the force that the pie does on the hand is the same as the hand on the pie. It's just that because the structure of the pie is much less strong than the hand, and the hand is what keeps its shape, and this is what gives way, right? But if I did it against the wall, and the wall's got a stronger structure than my hand will probably feel much more the change in shape and the damage than the wall, so that would hurt, right? And another way of understanding this law, which is really a good way of thinking about it, is that imagine that I try to punch with my huge ugly fist, I try to punch a piece of paper. Try to punch a piece of paper, and somebody's holding it here. Okay, it's held up here by someone with their hand, but they don't hold it here at the bottom, they're just holding it here, and you punch it and you try to break it, but you find that whenever you punch it, it just folds and it just gives way like that, and it doesn't break, and you can't, doesn't matter how hard you punch it, it doesn't really break. That's because you can only put as much force on the paper as it puts on you, and since it's free to move back whenever you try to hit it, the paper moves backwards and doesn't put a lot of force on your hand, and therefore you can't put any force on it, so it doesn't snap. You can't hit it that hard, it just gives way. They use that principle in martial arts a lot, when they give way and they sort of bend in when they're being hurt, and then they can't be then they're not opposing resistance to your punch, so your punch can't hurt them. Right? There's nothing more annoying trying to punch the air or water or whatever, because it kind of gets out of the way when you're trying to punch it. But if somebody held it here with 2 hands, they held it there in place, then there would be, the paper would try to put force against the hand. It would try to oppose, and then the hand could do more force on the paper, and it would most likely just punch through it and break it, right? And that's because the paper now is able to provide some force back, and the hand will win there. But in this case, it just bends, and it just you won't be able to hit it. So that's Newton's third law. The paper pushes back on you as much as you are able to hit it, and the other way around. You're only able to hit it as hard as it pushes back on you. That's also the way that rockets work. So rockets, if you've got something like this, and your rocket is like that and points up, it's gonna give off, then you throw a lot of stuff out, and all the force that you're putting on of this huge amount of fuel that you're letting go every second is the same amount as the force that the particles that you're releasing puts on the rocket. So the rocket, using by that change of momentum, or that change of that force that you're implying onto all of this gas, it puts on all of that. So this is much heavier than all these particles, but since you're expelling millions and millions of them every second, then this thing starts accelerating in that direction, and all of these particles accelerate in that direction, and they're equal and opposite forces, but they act on different objects. Again, this one acts on those guys, and this force acts on this guys. That's why it works. What else? Another way of thinking about this is if you had a hose. If you have a hose like that, and it's putting out water. I don't know why the American accent comes out there. And it's putting out water, then the hose will start doing this kind of snaky thing when you let it go, right? It starts moving around. And what's moving the hose? Well, it's Newton's third law. It's what Newton's third law is talking about, which is all the force that you put on the water, and as pushing it out, the water is also putting on the hose as it comes, so it pushes it backwards. Same thing with a gun. You've got a gun or a shotgun, and you fire it, and the moment the bullet comes out in that direction, the whole gun goes backwards into your shoulder. It's just that this is so much heavier than the bullet that the bullet goes off at an amazing acceleration, and this one goes back with a smaller, but you can still feel it pretty hard, acceleration. And that happens also because of conservation of momentum, but that's got to do very much with the same idea that forces have an equal and opposite direction. They always come in pairs. And finally, the last one that I wanted to mention was that if the sun is here, and it's absolutely huge, it's very hard to know the size. We'll talk about that in some other, I think, when we talk about astronomy a little bit. And this is the Earth here. Then the force with which these guys attract each other are equal and opposite. So this guy attracts on the Earth. It's huge and it's really far away, but it still attracts the Earth with a pretty strong force. That's why the Earth keeps going around the sun all the time, and the sun is moving through the galaxy, and everything is moving, so the whole thing really looks like a spiral like that going forwards. But that's not so important now. And what I'm trying to say is that the Earth is also pulling on the sun in that direction, and the forces are equal exactly. It's just that because this guy is so much smaller, his motion is much more affected by the force than the sun's motion is, but they're both exactly the same size, and they're in equal and opposite, and they're on different objects. Okay, so hopefully that helps, and yeah, we'll go on to the next question in the next video.